So in this video I want to deal with the alpha and beta anomers that we see in a lot of sugar molecules. And this is a question that I received from a student, and I figured that many of y'all have this type of question, so let me just go ahead and address it for everyone. First off, let me just draw one of the anomers. So let me do alpha D glucose here. So the D glucose portion, I mean, really what that's telling us is sort of this portion of the molecule. The alpha is telling us how the hydroxy group is pointing at the number 1 position. For the D glucose, what we see is this pattern of the substitution groups, or the functional groups that are attached to the ring here. It takes on this particular pattern where the CH2OH is pointing up, and then the OHs, the hydroxy groups, as you go counterclockwise around the ring, then they go in this alternating pattern where this is on top, this is on bottom, this is on top, and this is on bottom. And this particular pattern is unique to glucose, is unique to D glucose. If you change any of these orientations, then you have a different sugar. Now the alpha portion is in reference to what's happening at the number 1 carbon. Okay, so just a little reminder about the numbering. Okay, so it is a hexose sugar. Alpha tells us that the OH group is pointing down in this case. Now what happens is that, well, all of the monosaccharides we see in this class and 2 of the disaccharides will undergo this kind of process. And one way to think about this is that this bond here is weak. This bond can break and open up. And when it opens up, and kind of getting at this idea of an equilibrium, it'll actually go through this sequence. Whoop. It's in a sense a set of reactions that takes place for the glucose molecule, but really I can do this for any of the sugars. The relative pattern of the hydroxy groups in the Hayworth structure versus the Fischer projection, I'll deal with that later. In the Fischer projection, what we see is this pattern for the hydroxy groups. Again, if I extend the numbering out on this, so there's our 1 through 6 carbons. And so notice what's happening here is that oxygen up there is actually that oxygen there. And then this oxygen is that oxygen. Right? So what happens is that there's a reaction that takes place between this oxygen and that carbon, and that produces the ring structure that we see here. All right, 1 through 5 plus that oxygen, 1 through 5 plus that oxygen. And this Fischer projection would be known as D glucose. So notice the absence of the alpha or beta term. Now it doesn't stay in this Fischer projection, it actually goes to react further. And for the purpose of this question, really, let's pretend like it's definitely going to go just in the forward direction. It's fine. Because the equilibrium signs here actually mean that it's going to alternate back and forth, but we'll go in that direction. So if I have the alpha here, well, let me just do the beta here. And the reason it can actually do this is because it's in this equilibrium, that it's, has a weak bond, it can open up and then reform to something else. Now again, the D glucose portion is in reference, just like over here, reference about how the groups were arranged, well, from 5 to 2, the 2 to 5 carbon range. And this doesn't change. The only thing that changes is our beta orientation. Alpha's pointing down, beta is pointing up. And again, this is possible because it's undergoing this equilibrium reaction. In solution, the approximate percentages is something like, I think this is coming in about 66% approximately. This is coming in at approximately 33%. And then this is less than 1%. And the molecules are basically sort of constantly moving back and forth between these different forms. That's what an equilibrium is. So again, just sort of directly dealing with this question, right? This process of opening and closing, yes, that is what allows it to switch between alpha and beta. And by the way, just sort of as an extension to this, when we have this process occurring, this is known as mutarotation. And when we have mutarotation, what we do is we get a positive Benedict's test, which is discussed in the textbook as well as in laboratory. Briefly, it's an oxidation reaction where the solution turns from blue to red. It's a really common reaction you see for these carbohydrates.